Yo, what's up? This is Fundamentals of JavaScript Processing. Now, this is a really important topic towards front-end engineering overall. This is what's going to kind of get you to see the much larger picture, and you're not going to be able to really study this, I think, on your own without, really pursuing it. And it's something that's going to differentiate you from somebody that just jumps in and understands the syntax behind JavaScript and somebody who's an expert, somebody who can see what the general picture is, why we're doing certain things. And so basically in this talk we're going to see why we have what we have in JavaScript, which is things like what we saw in the Philip Roberts talk, the event loop. Why do we have that? Why is JavaScript single-threaded? Why is it called concurrent? And we're going to basically try to answer those questions and see different alternatives towards that. Okay, so in most programs, and you probably know this, is that a large part of it is how do we make answering the question of how do we make our programs run from beginning to end as fast as possible. And that's obviously without sacrificing things like extensibility of that program or readability of the code or things like that. But basically, this is a really important goal. How do we get it to run fast, right? Now, in blocking, in synchronous programming, in languages like C and Java, you have a main function. You might already know this. This might be very obvious, but it's like the entry point of your application, and it runs from the beginning of your program to the end. So any other functions are called from within main, and any threads are generated from main. Now this is really similar in asynchronous programming, except that main, in our case, is going to be called UI, our UI thread, and in Philip Roberts' talk is that single function call stack. And the really fundamental difference here is that one runs for a shorter period of time and one runs for a really long period of time. Obviously, non-blocking programs run for a much, much longer period of time. Let's take a quick example. So if I go to my terminal, this is a blocking program, right? So if I write something like ls, I just ran the program and it just finished. So basically what ls did was it looked at what I had in my hard drive, tried to figure out what files are inside the directory that I'm at, and then listed them on my screen. And then it's done. Input in, and then the output is pretty much the files, right? So the difference is from that and something like slides.com, which is a non-blocking program, right? Because slides.com is still a mainly JavaScript focused kind of application, right? Is that it started from the point that I hit this website, and it does not stop until I quit the website. I might be here on this website for 5 minutes. I've actually been on it for 4 or 5 hours now, and basically that's the difference. LS ran for maybe less than a third of a second. This is running for hours on end, and that's the way it is for most UIs. And you have to take that into consideration when you're designing your applications and so forth. So in blocking programs and in non-blocking programs, you have something very similar called the function call stack, right? So let's just quickly go over what that looks like in a single-threaded synchronous program. You have a function foo, and I'm writing it in JavaScript just because it's kind of like what we know. Foo calls baz, but baz also depends on cad. So we call foo down here. So foo is going to put that at the top of at the bottom of the stack, and that's going to call baz, and then it's going to layer on top of that with cad. And during that whole time, main is running, just to drill that point in. Okay, and just a stack top of the stack is gonna be the function that completes first. Cool. So the question is, how the hell do we make this thing run faster? What if I have to call foo 1,000 times? What if I have to call it 500 times? In our case, let's take the case of what do we do if we call it 3 times, and they're all independent of each other, meaning they don't depend on each other. One call to foo does not depend on the second call to foo. Really simple way to do that is by writing a multi-threaded program, right? So instead of having one stack, we would actually have 3 stacks: stack A, stack B, stack C, and these are basically 3 different threads that are working with 3 different stacks. So when you have a separate thread, you ultimately do have your own stack in that thread. And this is really good because if we're calling foo like this, in version 1 we were calling them one after the other, and in version 2, in the one that I just showed you, in the multi-threaded program, you can run them in parallel, right? You can basically shorten the duration in which the execution of the program is, and we're going back to our goal. This makes our program run much faster, right? So we actually, this is all great, but we see a problem when your threads are not independent. What if like foo is codependent on each other? What happens if they all want to access a single data structure? In our case, let's call this purple thing a hash table, okay? This hash table is accessed by every single call to foo. What the hell do we do then? If we have 3 threads and 2 of them or 3 of them try to access the hash table at the same time, you essentially have a case where you're struggling with atomicity. Basically, how do we know that every single one is happening perfectly even though they're happening at the same time? This might be kind of obvious to you, but it's a really tough topic, and you really essentially have to start diving into things like locks. So maybe thread 1 will, while it's accessing the hash table, it needs to lock that data structure until it's complete and then stack, and then thread 2 can access it, and then thread 3 can access it. And every single time you have to lock the hash table and unlock the hash table, and you run into things like permissions, and they're like very complex there's very complex terminology and topics about how do we synchronize these threads. And you also have another problem of basically race conditions. What if thread 2 is meant to run after thread 1? How do we make sure that that happens? How do we control like lower level like CPU operations like that? And that is really a very, very tough topic. So let's just quickly go over pros and cons of this, of synchronous programming. First is they're typically easy to reason about. Typically, you run one line of code after the other. So the line of code before ran before the line of code that came after. It's really simple. Blocking programs are okay. So your program might run slow, but it's going to run. As long as your code is not buggy, that's fine. Like an optimization is an optimization, but it's not a make or break thing. Now in UI engineering, in front-end engineering, that is not the case. You can't have blocking programs. And hopefully this point becomes clear to you as we go along. So the third point is similar to the second point, which is that execution can continue as long as any thread is not blocked. Okay. Now the cons: deadlocks, semaphores, basically the hash table, the thing that we were talking about before, the hash table. It's complex because suddenly you have to start synchronizing your threads, and you can run into things like the second point, which are race conditions, or you have to start managing the memory of the threads. Now we have a lot more memory now, and so it's not as big of a problem, but nevertheless, organizing threads and like trying to get them to run at the right times is a really complex thing. I'm actually doing it in one of my projects right now, and it's just taking forever.